Hey, welcome back, Warhawks. It's Mr. Martin again. You're getting a double feature, doing two of them back to back. So we're going to go over three forms of proof, and we're going to talk about different properties. She's actually been using these properties for a little while. We're going to go over different types of proofs. Hopefully, these are some things that kids always get scared about. We're going to make this not such a big deal, and then we're going to go over some more theorems. All right, so addition property of equality. You use this in algebra all the time. This is how you move something from one side to the other, or you can actually add things in whenever you want. So as long as you have A equaling B, you are allowed to add C to this side as long as you do it to the other side. You've been doing that ever since you started taking algebra. And just like you can add something, you can also subtract it. So we have addition property of equality, subtraction property of equality. If A is equal to B, then you can subtract C from this side as long as you subtract C from the other side. That's that thing where we say if you do it to one side, you have to do it to the other. We're actually giving them formal names, and addition property of equality when you add, subtraction property of equality when you subtract. All right, reflexive property. This is when you look at your reflection, you're seeing who you are. That's what happens when we use the reflexive property. We use this to say things are congruent to themselves. So X is congruent to X. That is the reflexive property. Or if we have line segment AB is congruent to line segment AB. We would actually do that. We use this in proofs. We're going to do that in just a little bit. We call that the reflexive property. So anytime you have to use that to prove that two things are congruent to themselves, you say reflexive property. All right. Substitution property is when you take something out and replace it with something that is equal. You've done this again for a long time. If I say above that x equals 5 and I say x plus 5 equals, and then you take out the x and you put a 5 plus 5, you changing this x into a 5 have done substitution. Substitution, if you like sports, obviously the coach calls a timeout, and if he takes a catcher out of baseball, you put a catcher back in their place. You substitute. You put something that's the same value in there. So substitution, teachers, you take another teacher out, you put a different teacher in, that same kind of thing. You're taking the x out here, and you're putting a 5 in because they're equal right up there. Transitive property is probably one of my favorite ones. I had a great teaching moment in one of my classes. So transitive property says if A equals B, so you have A equaling B, and B equals C, then A has to equal C. If Sarah is a girl, and girls are stupid, then Sarah is stupid. Actually, I had a girl in my class who could not get this property down, and I had to use a property example like this. I actually used her name, not Sarah. And from then on the rest of the year, she would go around saying, oh yeah, that's the transitive property because I'm a girl, girls are stupid, so therefore I'm stupid. And I'm like, yes, she finally got it. So it's when you can take this first thing and we apply that she is a girl. Well, we know that girls are stupid, therefore that makes Sarah stupid. That's the transitive property. Obviously, I'm not saying that girls are stupid. It's just supposed to be a joke. Proofs. This is where we get into some of the things that geometry we will be using throughout the entire year. There's different types of them. It's a logical series of statements and corresponding reasons that begin with a hypothesis and go to a conclusion. And anytime you're in a proof, you're starting at that hypothesis and working your way to an end, but you're just telling them the reason you're doing what you were doing. In math, we used to solve algebra, and you would do x plus 5 equals 10. And then you would subtract 5 and subtract 5. Well, now, instead of just subtracting 5, you'd have to write here, subtraction property of equality. We just went over that. So now I'm just saying the reason I'm doing that is because the subtraction property of equality. You're going to have to write that down. So instead of just doing the process, you also have to say why you were able to do that. And there's different kinds. There's paragraph, there's two column, there's construction. We're not going to go over too much construction because we're saving constructions till the end, right before that EOC. And then we have one called flowchart. So here's an example of what a two-column proof looks like. If you see, I know it's pretty blurry, so just bear with me, please. If you see this statement, you always start with the givens. We'll get into some examples in class, and you always write the givens down first. Get those out of the way, and the reason is they were given to you. They were part of the problem. Then if you know this is going to be, they're also going to give you this right here, which is going to be your conclusion. They will give you that in the problem. You've got to fill all the rest of this in based on the stuff that we've taught you. And this over here, you notice all these are the definitions, or they are theorems. That's why we've said vocabulary is so important in geometry, because they're going to be your reasons why when we do these proofs. So just like I did in the example before, you're going to show, like, here's step 2. When you go to step 3, you're going to do step 3, but you also have to tell why you did step 3. You're going to go to step 4, then you're going to say why you did it. And the theorems, the postulates, the definitions, those properties of equality, we're going to use all the time. In fact, we talked about substitution, where you take something out and you plug something in. In this step right here, they actually did substitution, and so that's why that was there. We also have done the angle addition postulate. They're using that right there. So there's actually some properties that we've already used being used in this proof. I don't want to go through this whole thing because we haven't used alternate interior angles. We will be very soon. But those are examples of a 2-column proof. You just put your statement on one side of this is how to do the problem, kind of, and then this is the reason why you're doing what you did in that next step. Paragraph proof is the same kind of thing, except you take this 2-column proof that you have right here, and you are going to put it actually in a paragraph form. You are going to say that this equals this because they is given to me, and then you're going to say, and these two are congruent because they're the same segment. So you're actually going to write it out. So you could take a 2-column proof, which we have right here, and just put some words in between the steps, and you have what is called a paragraph proof. So not too much different, just in the way that it's presented more than anything else. The process is going to be still the same. Next, we have a flowchart. Flowchart's a little different. We're going to get into this. Our book actually is going to start with the givens, not written. They're not going to write it horizontally. They're going to write it more vertically. So you're going to see the givens up here, and you'll see 3 circles, and then you'll see the arrows pointing down like this, and then a circle here, or all 3 of them. Actually, if I was doing this one in the book, okay. The book was given this example. Sorry, that was my eraser dropping. You'd have 3 circles at the top. You would have them all pointing to this one circle in the middle, and then you have another circle. So that's how the book would write this flow chart proof. Notice you always start with the givens, and again, you have what your step is and then your reason why. What your step is and what's your reason why. Your step is and what's your reason why. So very similar idea of what is going on, just different ways of displaying the information. But you should still get the same end results. All right, we got our theorems, and then we're almost finished. Congruent supplement theorem says if 2 angles are supplement to the same angle or congruent angle, then the angles are congruent. So here's what this says. If I have this as angle 1 and angle 2. And then over here, I have again angle 2, but this is angle 3. Congruent supplement theorem says, hey, 1 is supplement with 2, and 3 is supplement with 2. That means that angle 1 has to be congruent to angle 3. They have to be the same measurement. Congruent complement theorem is the same thing. The only difference between these two with this supplement and the complement is, hopefully you realize that this is complement. That means it's not going to add up to that line. I'm not going to do this. It's going to be a 90-degree angle. And so again, we can use 1 and 2 here, and then over here we can use 2 and 3. And that says because 1 is complement with 2 and 3 is complement with 2, that means that angle 1 again has to be congruent to angle 3. Remember, these numbers can change. This is not the only way to name an angle. I can use A, B, C, and D and name the points. That would take a little bit longer, but that is also a possibility. All right, last one, very simple. Vertical angles are congruent. They're always going to be congruent. So again, if I draw something like this, Angles 1 and 2 are going to be congruent because they're vertical angles. 3 and 4 are going to be congruent because they are vertical angles. We will use vertical angles throughout the entire year, so please remember vertical angles, keep that locked away, and use it throughout the entire year. That's it for this lesson. Hope you have a good night. I know that last night was a little bit longer, so I made up for it tonight, made this a little quicker. Have a great night and enjoy your sleep.